In this video, we're going to introduce the topic of bonding in molecules, introducing a topic called the localized electron model. This model of chemical bonding applies to covalent or molecular compounds, so we're going to be looking at bonds between non-metal elements, and it basically suggests that those chemical bonds can be viewed as shared pairs of electrons, or perhaps more precisely shared groups of electrons. A single bond is a shared pair of electrons, a double bond is two pairs of electrons being shared, and triple bonds are three pairs of electrons being shared. These are valence electrons within atoms, so we're going to focus on only the valence electrons as we go forward. There are three major subtopics in this model. We're going to look here at Lewis electron dot diagrams, also known as Lewis structures, named after Gilbert Lewis. Once we've mastered that topic, we'll then use those to predict the molecular geometry. So we're going to use something called Vesper theory, valence shell, electron pair, repulsion theory, to predict molecular geometry. We'll use the Lewis diagrams along with Vesper theory to predict geometries. Finally, we'll try to explain those geometries by something called orbital hybridization. We're going to try to save the view that valence electrons are in atomic orbitals, but to explain the geometries that we see from Vesper theory, we're going to have to take atomic orbitals and hybridize or blend them to create new sets of hybrid orbitals in molecules. So let's jump in with the Lewis diagrams. Lewis electron dot diagrams, Lewis structures. Basically, a Lewis diagram, its only real purpose is to show the connectivity within a molecule. By that I simply mean what atoms are connected to which other atoms in the molecule, and to show bonding and lone pairs of electrons. And we'll see what that means in just a minute. Specifically, the valence electrons within those atoms, within those molecules, rather. To start with, why don't we draw some Lewis diagrams for elements. Okay, so a simple diagram for elements. So we're focusing on the valence electrons. If we start with the simplest atom of them all, hydrogen, if you have a periodic table beside you as we do this, that would be great. Hydrogen, as you should know, has one valence electron, so we can represent that electron by just putting a little dot like that beside the hydrogen atom. So a Lewis dot diagram, or Lewis electron dot diagram, the valence electrons are represented as dots. So there's the Lewis diagram for hydrogen, very simple. We do the same thing for a carbon atom. If you look on your periodic table, carbon element number 6 has 4 valence electrons. We know that because its configuration ends in 2s2, 2p2, so it has 4 valence electrons in energy level 2. When we put those on the atom, I'll put them sort of as we go around the points of a compass, 1, 2, 3, 4, like that. Bromine is a halogen. The halogen family is in group 17 on the periodic table, and their electron configurations all end in s2 and then p5. For bromine, that would be 2, 3, 4 s2, I guess, and 4 p5. We have 7 valence electrons, so we'll start like we did before, going around the points of a compass, 1, 2, 3, 4, and then we'll start pairing them up. 5, 6, 7. So there's the Lewis diagram for bromine. Just to be clear, the electron configurations are not required for the diagram, just the picture with the dots around it. Now, basic elements, straightforward. What happens if we look at simple molecules? So again, we're looking at molecular compounds. These are covalent, which means only non-metal elements should be involved. Perhaps the simplest would be a hydrogen molecule, H2. We know it's simply two hydrogen atoms bonded together. And I can draw it like this with a single dash, or if you really feel adventurous, you could put two dots like that as a connection, a bond between them. We start every Lewis diagram for a molecule by simply connecting the atoms in the molecule with single bonds, and we may have to increase that to a double bond or a triple bond at some point, but basically that's how we start. With hydrogen, if we count the valence electrons, and we're going to do this for all of the later examples, we have two hydrogen atoms in this molecule, and each one of them brings one valence electron to the molecule, so we have two electrons to play with. We've used those two electrons right here in the single bond. It is two electrons being shared. Okay? Since we only have two electrons, we're done. Hydrogen follows what's called a duet rule, in that it's satisfied in molecules when it has two electrons around it. A single hydrogen atom had one valence electron, but when it forms a bond with itself, or as we'll see in a minute with other atoms, it tends to have two electrons around it now. Each of those hydrogens is sharing the same pair of electrons, so this pair of electrons can be thought of as being belonging to both atoms. Most atoms, though, don't follow a duet rule. They follow what's called the octet rule. If you're in period 2 on the periodic table, so elements from boron to neon, or as we'll see, always carbon to neon, but we'll throw boron in here for this discussion. Remember, we're focusing only on the non-metal elements because we're talking about covalent or molecular compounds. So these guys they follow what's called the octet rule, meaning that they're satisfied when they have 8 electrons around them. A simple example of that would be methane, CH4. If we start by just drawing the connectivity, so we have carbon surrounded by 4 hydrogen atoms. Now we should make a note here. In most situations that you will see in AP chemistry, the first atom in the formula is considered the central atom. There's a central atom here, carbon, then that central atom is surrounded by these others, so the 4 hydrogens. Now you can easily imagine much more complicated molecules, but we're going to stick with this basic, simple approach. When we do our valence electron counting, we have one carbon atom, and a carbon atom, as we saw earlier, has 4 valence electrons, so it brings 4 electrons to the molecule, so carbon atoms are bringing a total of 4 electrons. 4 hydrogen atoms, each one brings 1 valence electron, so together they're bringing 4 electrons to the molecule. So in this case, we have a total of 8 valence electrons to be using. In simply connecting the atoms like this, and remember that's one of the basic reasons we draw a Lewis diagram, to show the connectivity, we've used with the 4 single bonds already 8 electrons. So each of those bonds is 2 electrons, so 2 times 4, we've used the 8 electrons that we brought to the molecule. So in doing so, notice that the carbon atom has now 8 electrons surrounding it. it's got 4 bonds, each of which has 2 electrons. So that means the carbon atom is obeying the octet rule. The hydrogen atoms, though, have only 2 electrons in each bond. So for each of the hydrogen atoms, they're still obeying the duet rule. Another simple example to start with as we look into Lewis diagrams would be the ammonia molecule, NH3. Why don't you pause the video and try drawing this Lewis diagram yourself. The nitrogen is our central atom, and I'll draw my 3 hydrogens connected like this. Now, how I connect the hydrogens isn't important other than that they have to be connected to nitrogen. So if somebody wanted to put a hydrogen above and 2 off to the side, that would be perfectly acceptable. If someone else wanted to be more symmetrical like this, that would be perfectly acceptable as well. In a Lewis diagram, and this is really important to remember, the shape, the geometry, the angles of the bonds is not important. What is important in a Lewis diagram is simply that things are connected in the correct ways. So here's the 3 hydrogens bonded to nitrogen in ammonia. You remember the first atom is considered the central atom in almost all situations. If we count our valence electrons, we have 1 nitrogen atom, and nitrogen, its electron configuration ends in 2s2 and 2p3, so that means it's going to have 5 valence electrons. So nitrogen is bringing 5 electrons to the molecule. We have 3 hydrogen atoms with 1 electron each, so a total of 3 valence electrons from hydrogens. So by coincidence, we have a total again of 8 electrons to play with. Already, we've used 2, 4, 6 of those 8 electrons. So if I just take away the 6 that I've already used with my single bonds, we have 2 electrons remaining to be placed in the molecule. The hydrogens right now are all obeying the duet rule. They've all got a single bond, which means we can't add more electrons there. But the nitrogen atom in the middle currently has just 2, 4, 6 electrons. So it's not yet got an octet. To satisfy that, I'm going to put the remaining 2 electrons as a pair, like that, on the nitrogen atom. So that is now referred to as a lone pair of electrons. When you have a pair like that that are by themselves, we call that a lone pair, and that's going to be very important later. Contrasting, these electrons are called bonding pairs. So there are electrons, valence electrons, that are involved in bonds, bonding pairs. There are valence electrons just sitting by themselves as lone pairs as well. So there's the ammonia Lewis diagram. Water is another very common molecule. It breaks the rule that the first atom is the central atom. In water, or as we'll see later in hydronium ions, H3O positive, the oxygen is actually the central atom. In 99.9% of the molecules you'll see, the first atom will be central. But water is an exception, so we'll just draw the O with the 2 H's attached. So now the valence electron counting, we have 1 oxygen atom. There's 6 valence electrons for oxygen. Its electron configuration ends in 2s2 and 2p4, so a total of 6 electrons. We have 2 hydrogen atoms. 2 times 1 electron each is 2 electrons. And again, by coincidence, we have a total of 8 electrons to play with. We'll see very soon that that's not always the case. We've already used 2 and 2. We've already used 4 electrons, which means we have 4 electrons left to place. The hydrogens each right now have single bonds, so they're satisfied with duets. The oxygen in the center, though, has just 4 electrons currently. It needs another 4 electrons. So we're going to take these 4 and place them on the oxygen in pairs, and that's important. Always place them in pairs. And so we can see that the oxygen atom here has 2 lone pairs and the oxygen atom has 2 bonding pairs also. So this is on the oxygen in the water molecule. So there's some basic introduction to Lewis diagrams. If we jump up a little bit in complexity, let's take a look at an oxygen molecule, O2. Okay, if you want to pause the video here and try drawing this guy's Lewis diagram, that would be great. So we have 2 oxygen atoms. This looks like it should be easy. There's 2 O's, so 2 times 6 valence electrons. We have 12 electrons to play with. We've already used up 2 in this bond, so if I take away those 2, we have 10 electrons left to play with. But notice each oxygen has just this pair of electrons that they're sharing, so each one currently needs 6 more electrons to get their octets. That means we'd need 12 electrons total, but we only have 10. If you need more electrons than you have, that's the sign in a Lewis diagram to start introducing higher order bonds. So instead of a single bond, let's try a double bond and see how that helps. So we're going to have to take away 2 more electrons. We have 8 electrons left. And now notice, because we have a double bond, that represents 4 electrons being shared. So each oxygen currently needs 4 more. And we have 8 electrons left. We can place those 4 on each atom in pairs like that. So in oxygen O2, there's a double bond between the atoms, and each atom has 2 lone pairs as well. If you feel you understand that, then try pausing the video and drawing the Lewis diagram for nitrogen gas N2. In a similar situation, we have 2 nitrogens bonded together. Nitrogen brings 5 electrons, so we have 10 electrons total to play with. We've already used up 2, so we have 8 electrons remaining. Each nitrogen needs 6 more, so we need 12 more electrons, but we only have 8. So that's a sign to start putting in higher order bonds. We'll start with a double bond. So we'll take away 2 more. We have 6 electrons left. And we're still not going to be able to do this because each nitrogen now needs 4 electrons, so we'd need 8 electrons in total, but we only have 6. So we'll go up 1 more level and put a triple bond between the nitrogen atoms. Taking away 2 more electrons, that leaves us with 4 electrons, and we can now satisfy the octet rule by putting 2 electrons like that on each atom. So there's 1 lone pair of electrons on each atom, and a triple bond in between them. You remember, triple bonds are really strong. They're shorter than double bonds. Double bonds are strong and shorter than single bonds. So single bonds are the weakest, they're the longest bonds. Triple bonds are strongest, and they're the shortest bond. It's worthwhile memorizing that nitrogen has a triple bond, oxygen a double bond, and then the other Hofbrinkel elements, H2, we've already talked about O2, so fluorine, bromine, iodine, nitrogen, chlorine. So this guy has a double bond, this guy has a triple bond, and everybody else has a single bond in those diatomic Hofbrinkel elements. If we try and add a molecule now which has a charge, so this is really a complex ion, NO positive, we start in the same way, N-O. We have 1 nitrogen, so 5 electrons is being brought to the molecule from nitrogen, 1 oxygen, 6 electrons from oxygen. So it looks like we have 11 electrons to play with. However, this thing has a positive charge. The positive charge means losing electrons. In this case, we've lost 1 electron. So what I'm going to do here is take away 1 electron because of that positive charge, we have just 10 electrons left. We've already used up 2, and we can see that we're not going to have enough to give everybody an octet. If we put a double bond in, we've used up 4, we'd have 6 left. That's still not going to do it. A triple bond looks like it's going to be required, so if we take away 6 because of the triple bond, that leaves us with 4 electrons, and we can satisfy octets in a similar way to nitrogen. Now, one last thing, because this is an ion, you must put the Lewis diagram in brackets, square brackets, and put a charge outside. So always use square brackets and a charge for ions. Now, we subtracted an electron because this was a positive cation. If it were a negative anion, we would add electrons. So if this were 2 minus as a charge, we would add 2 electrons. If it were 3 positive, we would take away 3 electrons. So cations, you lose electrons; anions, you gain them. Another cation is the hydronium ion, acid-base chemistry, very important, H3O positive. We start with the oxygen as our central atom, remembering that that's the exception to the situation where the first atom is usually central. And we put the 3 hydrogens around it. We have 1 oxygen, that's going to be 6 electrons total. We have 3 hydrogens, so that's going to be 3 electrons total, so 9 electrons to play with. But because of this positive charge on the hydronium, we'll take away 1 electron. And so we have 8 electrons left. We've already used 2, 4, 6 in the bonds, so we have 2 electrons to give oxygen its octet. Because it's an ion, we'll put it in square brackets, and we'll put its charge outside the brackets. There's the Lewis diagram for the hydronium ion. So I hope you're feeling pretty comfortable now drawing basic, simple Lewis diagrams. There are a few exceptions to the octet rule. One which is just straightforward a memorizing situation, and that is BF3. If you try drawing its Lewis diagram, B, fluorine, 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 and you add up the electrons, 1 boron is 1 times 3 electrons, 3 electrons total, 3 halogens, fluorine, so 7 electrons each is 21 electrons total. We have 24 electrons to play with. We've already used up 6, 2, 4, 6, so we have 18 electrons left. Notice that each fluorine needs 6 electrons to get their octet. So if we start by putting 6 electrons around each fluorine in pairs, these are all lone pairs, we would use up the 18 electrons, and we wouldn't be left with anything for boron. Now, you might think, if you understood the previous examples, that perhaps we should try putting in double bonds. In fact, we could satisfy the octet rule by giving a double bond to one of the fluorine atoms. The problem is that when you look at the chemistry of BF3, it appears that that doesn't happen. In BF3, it's a highly reactive molecule, and the boron behaves as though it has only 6 valence electrons when you study it in the lab. So we say that the boron is electron deficient. Or another way to say it, it has a deficient octet. It has less than the 8 electrons that we would want to give it. So simply memorize that that is the Lewis diagram for BF3. Other exceptions appear when you reach atoms in periods 3 and lower. So we talked earlier about just period 2. carbon, nitrogen, oxygen, etc. But what happens when you get to period 3? We'll see the problem here is that if you're in a period 2, your valence electrons are in the 2s and the 2p sublevel. So for example, fluorine, 2s2, 2p5. 2s and 2p means that you can have a maximum of 8 electrons in those two subshells, right? 2s can hold only 2 electrons, 2p could hold up to 6, so we can never have more than 8 electrons, and thus the octet rule comes for period 2 elements. When you get to period 3, or 4, or 5, now you have not only the 3s and the 3p, but you also have the 3d subshell. The 3s we know can hold 2, the 3p can hold up to 6, there's 8, and that does often happen. But we'll see in just a moment that period 3 can have more than 8 electrons because of these d orbitals that are available for bonding as well. A simple example of this, a very common example, would be SF6, sulfur hexafluoride. If you try drawing its Lewis diagram, sulfur with 6 fluorines around it, you see right away that we have a problem. Sulfur has 12 electrons right now around it, and there's no way to connect the 6 fluorines to the sulfur without giving more than 8 electrons. So we say here that sulfur has an expanded octet. And the explanation for that is because it has these d orbitals available for bonding, it can actually have more than 8 electrons. You will only see expanded octets for elements in period 3 or lower on the periodic table, because that's where you'll see d orbitals available for bonding. Elements in period 2 can never have more than an octet. We saw boron had a deficient octet, but you'll never have an expanded octet for an element in period 2, because only 2s and 2p orbitals are available. Let's finish the Lewis diagram for SF6. We have 1 sulfur, so 6 electrons. We have 6 fluorines, 7 electrons each. So we have a total of 48 electrons to play with. We've already used 12, so if we take away 12, that leaves 36 electrons remaining. And we notice that each fluorine needs 6 more electrons to get their octets. So therefore, if we take these 36 electrons and divide them equally among the 6 fluorines, we'll give the fluorines, each of them, an octet. But the sulfur ends up with 12 electrons around it, therefore it ends up with an expanded octet. So notice we still start by trying to give the octet, but we're prepared for elements in period 3 or lower to give more than that if necessary. Alright. If we take a look at maybe one other example, and then we'll pause here. How about ICl4 minus? ICl4 minus. See if you can pause the video and draw this Lewis diagram. So iodine with 4 chlorines attached. We have 1 iodine, so 7 electrons from there. Valence electrons. We have 4 chlorines, so 7 electrons each, 28 electrons total. So that looks like we have 35 electrons to play with. However, remember that this thing is negatively charged, so we have to add, because it's -1, we'll add 1 more electron. If it were 2 minus, we would add 2 more electrons. So we have 36 electrons to play with. We've already used 2, 4, 6, 8, So if I take away the 8 electrons that we've already used in connecting the atoms, we have 28 electrons left. The chlorines all right now have just 2 electrons, so to give them their octets, they would need 6 more electrons each. If we do that, we have enough electrons. If we do that, we've used up 4 times 6, we've used up 24 electrons. That means we have 4 electrons left over that we have to do something with. When you have leftover electrons, the rule from the localized electron model is to put those extra electrons on the central atom. Remember that elements in period 3 or lower, and iodine is certainly one of those, it's in period 5 on the periodic table, they are allowed to have expanded octets. So these 4 electrons I'm placing on the central atom with 2 lone pairs. And finally, because the whole thing was an ion, we'll put its diagram in brackets and put a charge outside the brackets. So there's the Lewis diagram for ICl4 minus. Now, there's just a couple things left to discuss. We're going to talk about, in a future video, we'll practice some more Lewis diagrams. We'll talk about resonance, and then we'll talk also about the concept of formal charge before we can wrap up and look at the Vesper theory, which is the next step in predicting molecular geometries.